All right, folks, we're going to talk about section 3.4, and that is using the second derivative test in order to determine concavity. As you can see from the objective, you will be able to determine concavity, be able to apply the second derivative test, and also be able to determine some other necessary information related to that. Okay, the warm-up, I'm going to head and set up the warm-up beforehand, so that way you won't have to, we don't have to spend so much time writing. Okay. If the function f of x equals negative x to the third plus 9x squared minus 24x plus 18, we determine the critical numbers. Remember, you have to determine the derivative. The derivative, of course, is negative 3x squared plus 18x minus 24, which simplifies all the way down to negative 3 times x minus 2x minus 4, which means that our critical numbers are at x equals 2 and x equals 4. And then we got to determine where it's increasing and decreasing. Well, what we do here is we take an interval somewhere in between negative 0 and 2. I choose 0, to be honest with you. But if you plug in 0 into f prime, you're going to get a negative number, which means it's decreasing. And then somewhere between 2 and 4, I choose 3, just something simple. You plug it in and you get something greater than 0. That means it's increasing. And then for 4 through...
Good morning, and sorry to interrupt your day, but we are...
And then f prime is less than 0 to from 4 to infinity. One of the best ways to determine, so we don't have to plug in the numbers in on your own. If you just want, type in the equation into your graphing calculator and then just do the table. That's a quick way to do that. It may take a minute to set it up, but it's quicker in the long run if you do that rather than trying to solve each one of them individually. So to save yourself some time. Well, and it asks us to determine the extreme. Remember, the minimum is between where it's decreasing, it goes from decreasing to increasing. So therefore, at x equals 2 is our minimum, which is at the point 2, negative 2, when we plug it into the original equation. And then the maximum is at x equals 4, because that's where it goes from increasing to decreasing. So it's at the point 4, 2. All right, so that's that. Now, I want you to look at the following. We're not going to solve it or anything, but I want you to look at the concavity. Now, if you look at it from negative infinity to 1, it's concave downward. That means when I say it's concave downward, that means it's facing downward. On the other hand, from 1 to infinity, it's concave upward. That means it's facing up. So this is concave up, and this right here is concave down, arrow down, concave down. So that's what it's talking about when we're talking about concavity. That's the big thing I want you to get out of that. And let's look at concavity. All right. Now, the definition of concavity is this. Let f be differentiable on an open interval. The graph is concave upward if f prime is increasing on the interval, and it is concave downward if f prime is decreasing on the interval. And it says the same thing down here. I just have it worded a little bit differently up here. So if f prime is increasing, then that means it's concave upward. If f prime is decreasing, then it's concave downward. All right, so let you absorb that for a minute. Okay, now for this one, the following interpretation is useful. F be interval. If the graph is concave upward, then f, this is an example of concave upward, and you can look as here, f prime is increasing. It's facing upward. The concavity or the open part is facing upward. On the other hand, if it's concave downward, then you can see right there, f prime is decreasing. Like right there, f prime is getting smaller. All right, so the graph lies on or between the tangent lines. All right, now I'm going to show you a comparison between two graphs. Okay, this is the original equation right here. You can barely see it, but it's right there. It is, and I'm going to write it over here in blue. So f of x equals 1/3 x to the third minus x. That's what f of x is. Well, f prime of that, as you can see there, is x squared minus 1. Okay, so now notice from the same locations right here, I want you to look at the same equations right here, and I'm going to highlight these in a different color. I'm going to highlight them in orange. I hate orange. Actually, no, I'm not going to do that because it doesn't do too well. Well, here's what happens. This shows the original function. Notice that's concave down. It's still concave down to right there. And then right there at this change right there, it changes concavity. Now it's concave up. This is the derivative, or f prime of x. Notice how it's going down, then all of a sudden right there it goes up again. So if that's the same spot right there, all right. So f is concave upward on the interval from 0 to infinity because f prime is increasing on the interval. So as f prime gets bigger, that means that it's concave upward. So here we see that f prime is getting bigger. Down here we see f prime is decreasing. You tell that right there? And f prime is decreasing because as f prime gets lower and lower, it's going to continue getting lower. That shows that it is concave downward. But right here is when the concavity changes, and right there it goes from concave down to concave up. Right at this point. I don't know if that makes a whole lot of sense. We'll talk about it some in class, but I do want you to be aware of it. And I did post some other videos on it. If you want to look at those as well, I don't mind. But okay. Now, to test for concavity. All right. To test for concavity. The following shows the use of the second derivative. We're going to use the second derivative to determine the intervals from which f prime is concave upward or concave downward. So, if f prime of x is greater than 0, then the graph is concave upward. So we're going to take the second derivative. If f prime of x is negative or less than 0, then the graph is concave downward on the interval. All right. Now, okay. Example 1, f of x equals negative x to the second all over 2. The whole thing is over 2. Now, what I did was I went ahead and worked it out for you just because of time. But when you take the first derivative of it, it's going to be negative x times e to the negative x squared. But then the second derivative, it's going to end up giving you e to the negative x squared over 2 times x squared all times x squared minus 1, because what happens is e to the negative x squared is in each of the terms, so therefore you end up getting e to the negative x squared over 2 cannot equal 0 because it's an e function. It cannot equal 0, but x squared minus 1 can equal 0, so our x values are negative 1 and positive 1. By the way, these are what's called points of inflection. Points of inflection are where the concavity changes. So I set on the interval from negative infinity to negative 1, and then from negative 1 to positive 1, and then from positive 1 to infinity. I get my test values. It just shows negative 2, 0, and 2. You could choose anything you want, and then plug those values into the second derivative, or f double prime of x. And if it's greater than 0, you have concave upward. So if you look from from 0 or from infinity to -1, we have concave upward, which if you look, the graph is upward. And the same thing goes from 1 to infinity. It's concave upward. But on the other hand, when f double prime is less than 0, from -2 or -1 to +1, it's going to be concave downward, which is what you see right there. So, and another way to do that is if you don't want to have to type, if you don't have to solve each one of them individually, type in this function into your graphic calculator and just use the table function. It takes a couple minutes sometimes to program it into your calculator, but it saves you much more time and much more headaches down the road. So, but you got to be careful though, because if you just type one little thing wrong, it can throw everything off. All right, so we're doing pretty good on time, but all right. So a point of inflection is continuous on the open interval. Then C, the point of inflection of the graph is where the concavity changes from upward to downward or downward to upward at the point. Okay, so here are the three types of points of inflection. You got the concave upward, the concave downward. As you can see right here, it's up, now it's down. Here, concave downward to concave upward, or you've got this right here. These are just some examples of what you will see where it changes. But you can see here, concave up, concave up, concave up. And here, concave down, concave down, concave down. All right, so those are just some examples. Now the concavity changes at a point of inflection. Note that the graph crosses its tangent line at the point, and the definition requires that the tangent line exists at the point of inflection. Just some technical stuff you need to be aware of. But to look at the possible points of inflection, you could determine by where f double prime of 0 or the second derivative has a 0 value or where it does not exist. Very similar to the approach that we use to determine the points or the critical points or determining the relative extrema. Okay, I am going to go ahead and pause this for a moment, and we will continue this with part 2 of the video.